Okay, welcome back to CS 2040S. Let's get started. We are on to week 3. We are already at week 3 of the semester. Can you believe it? So let us get started and on to some new exciting things today. By the way, you'll notice I have over on Archipelago a poll asking for some nominations of pre-class music. I see currently we have a lot of Ricky Aston fans. So if that's what you'd like to hear, if that's really what you want, lots of people voting for it, we can do that. But if perhaps if you'd like something else, maybe go and vote for that or put in your own suggestions. And there's also you can also mention what you like over on Archipelago. It's over on the Coursemology forum. Okay, good. Let's see what we have. What happens in week 3? In week 3, we get problem set 3. Problem set 3 is going to be a little different from some of the previous ones. In problem set 3, your job is to be a detective, a sorting detective. You will have 6 suspicious sorting algorithms to investigate. Your job is to investigate the mysterious sorting code and identify each of the sorting algorithms. And your real goal here is to find the criminal Dr. Evil. Okay. One thing I will say in advance, this will make more sense as the lecture goes on, but focus on the properties of the sorting algorithms, the asymptotic performance, stability, performance on special inputs, and so on. That's how you are going to identify your sorting algorithms. I should warn you that absolute speed is not a good reason. So for example, some people on this problem set like to submit it and say, well, I ran all the algorithms and this one over here, Mr. B was the fastest. So Mr. B must be quicksort, okay? Or perhaps you compared 2 algorithms and said A is faster than B, so it must be InsertionSort or whatever, okay? This is not a good bit of investigation going on. In fact, the suspects here are a little deceptive in the sense that they will not necessarily represent their true speed. Okay, so you can't use absolute measurements as a way to determine which is which. Instead, what you have to do is look at how an algorithm runs on different inputs. You have to compare how algorithm A runs on this input versus how algorithm A runs on another input, and those you can compare. Okay, good. So in the end, your sort of report here, your evidence should be based on testing each algorithm on a variety of inputs. Okay, great. So good. That is problem set 3. It'll be released later this evening after class. Okay. Some other admin stuff this week. Recitations and tutorials start this week. All the assignments should obviously be done by now. Thank you for bearing with us and being patient for getting the allocations done. It's a challenging problem each year to get the allocations done, especially because we have very tight constraints. We really want to keep each of the groups at exactly the minimum size. We don't want some tutorials of size 30 and some tutorials of size 10. And whenever we use ModReg, for example, that's what happens. We get these large disparities where really we want every tutorial to be plus or minus 1 exactly the same size. And I think we've achieved that. And so again, thank you for being patient and bearing with us during that process. I know it's difficult and annoying for you all as well. But I think we've gotten something reasonable in the end. I think most of you have gotten something that's close to acceptable. So that is good. So tutorials. Most tutorials are going to have sort of 2 parts to them, sometimes clearly distinguished, sometimes unofficially. There'll be sort of a part with more sort of review of class the previous week, review of sort of easy questions to sort of check, are we all sort of caught up on what's going on here? And this week, in fact, I think most of the tutorial falls under that category. And then there will often be a second part which has harder questions. And the harder questions are the type of question that you may have to all work together in a group to work on. It may be that if you look at it yourself, it might not be clear how to solve it, or you might have some ideas, but you really need to, but it seems very, very hard to you. And these questions, the types of, questions where you should work on them, think about them before tutorial, and then plan to go to tutorial and work together on them. And same with recitation questions, by the way. Some of them may be hard enough that you have to go to recitation and work on them together, but it helps to think about them in advance. Okay, so here are the things to think about this week. First, step one, check with your tutor and make sure you know where you are supposed to be, whether in a room or on a Zoom link. A small number of the in-person sessions can't be in person this week due to room conflicts, unfortunately. So again, just make sure that you have the exact, you know where you're supposed to be. Your tutor should have emailed you with this information, but if not, reach out to them. Okay. Second, it is good to prepare in advance for the tutorials. If you go through the questions beforehand, then you will be better prepared and you'll be better able to contribute. Recitation Zoom links we will be posting on Coursemology later this week. And that will make sure is available to everyone. Okay, so do prepare in advance. This means also that if everyone is sort of on the ball, you can go through the easy questions quickly and get on to the harder questions. Or if you discover that the easy questions are not easy, then that's great. You can let your tutor know to spend some more time on them. So in particular, it's important to provide sort of continual feedback as to what's easy, what's hard, and help us adapt the pace properly. Okay. One of the things you should do while you are preparing is prepare some questions. As you go through the tutorial, look through the questions and figure out what you would like to ask about. Sometimes it'll be because you don't understand something. Sometimes it'll be because one of the questions inspires you to think of something else. Maybe you're curious about how something on tutorial connects to something from lecture. Think about in advance some questions that would be useful. Lastly, one of the main advantages of having tutorial is it's a chance in a smaller setting to get to know your tutor and some of the other students in the class. So I would encourage you to take advantage of this to try to get to know some people. Maybe you are a gregarious, outgoing person and love to meet people, in which case this seems obvious and clear. Maybe you're a little shy and especially over Zoom, find it hard to meet people. That's also fine. I would still encourage you to try to take advantage of these tutorials to meet people in your class. There are many advantages to this. One of them is just it's much easier to learn in groups when you have people to talk to. And in addition, these are people you can ask for ideas, help, suggestions when you're stuck, and so on. Okay, so try to get to know people in your class, in your session. Okay, great. Let's see, what else? Other items, that's all I have to say about tutorials. Again, go to tutorials. There's also a forum to discuss the questions and let me know how it goes. I hope it should be fun this week. Okay, next, the Treasure Island contest is ongoing. I'm not going to say any more about that, but just remember it closes Friday. So get your submissions in by Friday. Okay. Onwards. So last time we were talking about peak finding, and you may remember at the end I hinted at there's an interesting two-dimensional variant of it. I'm actually not going to talk about that today. I'm going to actually move on and leave that as an interesting question to consider on your own, or perhaps we'll get to it in a few weeks. For now, I'm going to postpone it and maybe revisit it in a couple of weeks if we have a little spare time in a few weeks to talk about a fun problem. I like to do this on occasion to sort of pause where we are in terms of lectures and go back to something earlier and sort of review it and look at a fun problem that uses that technique. So I might come back later this semester to peak finding as a short interlude. Okay, if you're interested in looking ahead, the 2D peak finding version is the natural extension of the one-dimensional version, where your goal is to find a peak in a two-dimensional array. Okay, good. So what are we doing today then? Today we are talking about sorting. We are beginning our whirlwind tour of sorting algorithms, which will be for the rest of this week and a little bit of next week. We are going to see all sorts of sorting algorithms. We will be seeing BubbleSort, SelectionSort, InsertionSort, MergeSort. We'll be seeing running time, space usage, stability. Later we'll be getting to quicksort. Lots and lots of different sorting algorithms there. Fast sorting algorithms, slow sorting algorithms, a whole variety. Okay. Much like with binary search, I suspect that a lot of you have seen some of these sorting algorithms before, or at least used them as black box pieces of code. So on the one hand, that's great. On the other hand, I hope we're going to go into a little more depth as to understanding why and how they work, and think about this from an algorithm design and analysis perspective. How do we choose among the various trade-offs available? Okay, so we'll be thinking about this from how to analyze a sorting algorithm, right? Given an algorithm, how do we analyze its performance? What are the invariants involved? Again, a key part of algorithm design is invariance. So we'll talk about the invariants. And again, we'll talk about the trade-offs. How do you decide which algorithm to use for which problem? Despite what you may think now, there is actually no one perfect sorting algorithm. There is no one sorting algorithm that you should always use. Sometimes one is better, sometimes another is better. And part of what I want to get at is how we decide which one to use in a given situation. Okay. So that's the plan for today. Good. Before we get started, I'm just going to check the random questions board to see if there's anything I should address. Okay, so I'm going through some of the random questions here. One of them, is there a due date for the optional missions? No, there is no due date for the optional missions. Okay, you can do them whenever this semester. Our advice is to do them as they open, which is approximately when we're covering that material, but we will leave them available the entire semester. Okay. Let's see. There's a question, what to do to get archipelago experience? You have to do nothing. We will be tallying it. We had some trouble for a couple lectures. I think we fixed it, but if not, we'll get to that. But you don't have to do anything. You just have to use archipelago. Okay. Let me see what other questions are up. Someone says they submitted their solution to problem set 2 last Thursday and it has yet to be graded. And how fast do we get to grading things? This is a good question and will depend a little bit on how difficult the problem set is to grade and how busy everyone is, because your tutors, of course, as you know, are also very busy. The maximum I ask is for things to be graded within a week. Ideally, things should be graded within a couple days. But of course, there's also been some delays at the beginning of the year because of getting everyone assigned to tutorial groups. So somewhere from 2 to 3 days to a week is the time frame that we should expect. And again, I'm sorry if things take longer, but please be sympathetic to your tutors who are themselves very busy with their own work. Okay. Where do we find recitation Zoom links? So posted on Coursemology. Is attendance taken for recitation? Probably. Let's see. Someone's worried about obtaining full marks on the problem set. I wouldn't worry so much about that. Remember, you don't need full marks to get to level 35. The goal is to learn stuff on the problem sets. So take advantage of when the tutor grades your problem set and points out certain things. Take advantage of that as an opportunity to learn something about how to do better. And you may think that it's, you may agree, you may disagree. Some people have argued with the tutors a lot. We are trying to give you the best advice we can as to how to write good code. And so you should try to take what benefit you can from that. As I said, in the end, almost all of you will end up at level 35 no matter what. Okay. Profile picture contest winner, that I think is still being tabulated, but will be announced soon. Okay. What is the maximum level for Coursemology if we finish it all? Well, again, above 35, it doesn't matter. Beyond that, it's open-ended and just depends how much experience you get. Okay. I'm seeing here. The question, can you use java.util.array whatever? In general, on the problem sets, as I've said, the rule is you should not use any of the Java libraries unless the problem set specifies that you can. Okay, so the problem set will specify for that problem set whether or not you can use certain libraries or not. The default is not. Anything you'd have to import, don't use. Okay, let's see. Okay, good. So I think that's it for the random questions for now. I'll come back to it later again and see if anything else shows up. But I think we are ready to move on to technical content. Again, sorry for the delay, but I do like to try to make sure that things are clear to people. So we are talking today about sorting. So before we get started, as always, we should try to make sure we understand what is the problem we are solving. In this case, I think most of you have a pretty good intuitive sense for what sorting should be. You're given some sort of input, typically an array. I guess today we're using 1 as our base of the array, so from 1 to n. You'll notice sometimes we have arrays from 1 to n, sometimes from 0 to n minus 1. Doesn't matter, just pay attention to what we are using for the given day. So we have our array of n inputs. These could be words, these could be numbers, these could be images, these could be books. Who knows? We have n things that we want to sort. And we want to produce a permutation of the input that is either increasing or decreasing, or non-decreasing or non-increasing, as the case may be. And so, of course, we have here at the bottom an example. We take our array of inputs, whatever here, and we put them into sorted order. Great. You will notice something about this example. This example has some duplicate elements in it, right? Whether or not we deal with duplicate elements, this is something to pay attention to. Okay, great. So one thing, of course, is we're not going to talk a lot about Java today, but when you get to the problem set, you will need an interface in order to work with these sorters. This problem set is actually a good example for the use of an interface. You don't need to know how the actual implementation works. You can still use these sorting objects. And so you could imagine something like a sorting interface that looks like this, where it just has one public method, sort, which sorts an array of integers. Okay. And of course, if you have studied a little more Java, you might realize that you might want to sort not just integers, but you might want to sort lots of other things as well. And there are actually mechanisms in Java for doing that, okay, for parameterizing your sorting interface. But we are not going to get to that here. Go see CS 2030, hopefully, for parameterized interfaces. Okay, great. As an aside, and as a warm-up to warm up Archipelago and get it going today, here is a famous sorting algorithm, BubbleSort. In BubbleSort, you choose a random permutation of the array. If A is sorted, you return the array. And if not, you try again. So run on over to Archipelago and tell me the running time of this, the expected running time of this algorithm. Okay. I talked to the Archipelago folks, and in theory, they're experimenting with something to see if we can get better performance this week. So I really want you to hit Archipelago hard this week, really hammer it so we can see if this is fixing some of the lag problems we are having. Okay. I see someone in the chat says worst case infinite. So yes, you will notice, by the way, that there was a key here that I said the expected running time, and expected here has a specific technical meaning. I'm talking about the expected value as a random variable. Okay, okay, great. So I see lots of answers in. I'm going to go on and not waste too much more time on this, but here we go with BubbleSort. The running time of BubbleSort, in fact, to the dismay perhaps of some of the answers here, is n times n factorial. Okay, so in particular, it's going to take n factorial time, n factorial iterations of the loop to, in expectation, get a sorted array, right? Every time I choose a random permutation, I have a 1 over n factorial chance of choosing the right permutation. Great, in the worst case, assuming all the elements are distinct. Okay, but of course, then I have to check if the array is sorted, and that takes an additional n time. Yes, I'm sorry if Archipelago doesn't have a retract button on it, but alas, it doesn't matter too much anyways. There's a question in the chat. Can we say the expected running time is always the worst case? No, we have to be careful with that actually, because expectation has to do with a random variable. Worst case has to do with the input. And so in fact, you get interesting combinations. So you can talk about the worst case expected running time, which is the expected running time over the worst case input, or you could talk about the best case expected running time and so on. Okay. And as a aside, or I guess something of a joke, someone once responded when I talked about BubbleSort, hey, what do you think of quantum BubbleSort? And I had to ask, what is quantum BubbleSort? And this student told me, quantum BubbleSort, this is where you choose a random permutation of the array. If the array is sorted, we return it. If it's not sorted, we destroy the whole universe. And I thought, haha. That's a fascinating idea. Interesting question of what the expected running time of this is. And this is, of course, entirely a joke. But in fact, when you get on to taking a complexity theory class or a theory of computation class, and you learn about non-deterministic Turing machines, you should come back and remember quantum BubbleSort. Okay. We're assuming here you could destroy the universe in constant time. Okay, good. Here is another fun question, which I will leave for you to think about after class. I don't think I'm going to give the answer of this one. This is another variant of BubbleSort, a little bit better than quantum BubbleSort because it doesn't destroy the universe. Okay, so just like quantum BubbleSort, we begin by choosing a random permutation of the array. Okay, but now instead of just checking if it's sorted, all we do is check if the first element is the minimum item. If the first item is the minimum item, we recurse on the rest of the array. Otherwise, we repeat on the entire array. Okay, so I'll leave this as a question for you all to discuss on the forum or to think about yourself. What is the expected running time of this one? This is a little more interesting, I think, than quantum BubbleSort. Okay, good. So now that we're done with our BubbleSorts, we can get on with our more usual sorting algorithms. Okay, let us begin with BubbleSort, everyone's favorite first sorting algorithm. Why do we teach BubbleSort? I'm not even 100% sure. It's a terrible sorting algorithm. You probably shouldn't be using BubbleSort for anything real, but it is often taught as the first sorting algorithm as an example of what not to do. I don't know, of an example of how to analyze sorting algorithms and how to think about sorting algorithms. And someone in the chat says bubbles are cool. Okay, so here is BubbleSort. We go through n times. We're going to repeat this whole thing n times. Each time through, we're going to scroll through the entire array from beginning to end. Why can't I draw on the screen anymore? There we go. We scroll through from beginning to end. Okay. And at every step along the way, we compare to the two adjacent items and swap them. Let me give you an example. Here is our array to BubbleSort. Okay, we start out, we compare the first two items, 8 and 2. We discover 8 is bigger than 2, so we swap them. Good. Onwards, we compare 8 and 4. We discover 8 is bigger than 4, so we swap them. 8 is less than 9, we don't swap them. 9 is bigger than 3, we swap them. 9 is bigger than 6, we swap them. We are now done with one whole iteration of BubbleSort. Now we have to repeat this 5 more times. Okay, this is pass number 2. We compare the first two items. We don't need to swap them. The next items, we don't need to swap them. We swap, we don't swap. That's iteration number 2. Then we go on to iteration number 3. Again, we go through everything. We have one swap more to do. Iteration number 4, we go through everything. Now there is nothing left to swap. Okay, we get to the end. That's great. We now have a sorted array. Okay, great. So that's BubbleSort. Everyone knows it, loves it, can implement it in 30 seconds. That's BubbleSort. Okay. You'll notice, of course, that we didn't actually need to repeat this a full n times. That's a bit overkill. Really, you just need to repeat until everything is sorted. So repeat until there are no swaps left. Okay. If you repeat until there are no swaps left, then you will be happy. You will be done. Okay. So this sort of optimization, I think, is sort of standard for any real implementation of BubbleSort. Okay, as we talked about last week, what we're really going to care about here is how an algorithm scales as the input gets large. So what is the running time on inputs of size n as n gets big? Okay, so here we go. Pop on over to Archipelago as soon as I can open the question on Archipelago, and tell me, what is the running time for BubbleSort? Hey, Archipelago seems to be doing a little better today. It should be open now. I just opened it. And I saw a little bit of lag as I opened it, but less than usual. So we'll have to see. It seems a little better than usual, but hopefully, yeah. If you can't see the question, then we are still seeing lag, alas. Okay. I promise you about 350 people have answered it so far, so it is open. It's just not showing up for you. Okay, so what's the answer here? The answer here is going to be n squared. Okay, in the worst case. In particular, we're going to have to go through n times in the worst case, and each iteration takes n time. Okay, so that's clear. That's not so hard. But let's see if we think about it a little more carefully. If we want to figure this out, instead of just sort of knowing the fact that it's n squared, let's see if we can be a little more precise. Okay, so the first thing to observe, someone joked last time that all the answers to every question this semester is it depends. It depends. This is a case, of course, where it does depend on the input. I see some comments in the chat being concerned about experience for Archipelago, by the way. As long as you participated, it doesn't matter if one of the questions goes by because of too much lag, okay? So you don't need to worry about that. We're not going to punish you for laggy Archipelago. Okay, so anyways, it depends on the input, okay? In particular, we know that if the input is sorted, BubbleSort is going to be very fast. Right, so here BubbleSort only takes one pass. We just go through the array from beginning to end. We discover that it's sorted, order n time, we are finished. Okay, this is the best case performance. This is the input on which it runs the fastest. Okay, on the other hand, you might care about average case performance. Right, this is the running time when the inputs are chosen at random. We are not going to do a lot of average case analysis this semester, but I think it's interesting. And there's some cases that I will point to because I think they're particularly interesting from an average case perspective. On the other hand, the problem with average case analysis is you don't always know the distribution of inputs. If in the real world, the inputs really are chosen at random, average case analysis is great. But in some cases, the inputs are not chosen at random. And so we want to look at the worst case, the maximum running time over all the possible inputs. Okay, so unless otherwise specified, this is what we mean when we ask for the running time. We always mean what is the running time on the worst case input. Okay, great. Okay, so if we want to sort of carefully analyze the running time of this, what we need to ask is how many iterations do we need until we are done? Okay. And one way to think about that, as always, is in terms of invariance. Okay, so in particular, here's a good question. If you were designing a BubbleSort algorithm, what do you think a good loop invariant is for BubbleSort? I have just opened that question on Archipelago. Hopefully it shows up for you this time. If not, try reloading Archipelago. Okay, so run over to Archipelago. And how about try typing in what you think might be a good invariant for BubbleSort? Okay, let me talk about a few of the options that I see people have typed in. Okay, so one person suggested that Archipelago can't correctly display anything after a less than sign. Okay, that's unfortunate. I see some less than signs. I don't know if people escaped them or not, but I certainly see some less than signs. Maybe it's not showing it to you, but it's showing it to me. I don't know. One person put in the answer of the array is size n as an invariant. Now, this is true as an invariant in the sense that the array is always size n. The array size does not change over time. So it is an invariant, but somehow it's not a very useful invariant because it doesn't really help us to analyze the algorithm. Okay. So in particular, for a loop invariant, we're most interested in invariants that have something to do with what happened during the loop, right? If it doesn't change anything, if nothing ever changes, then it's not very interesting. Okay. I see another person wrote something about, a couple people wrote something about no duplication or no duplicate items in the array. That I don't think is an invariant. There could be duplicate items in the array. Okay. A whole bunch of other people wrote things related to something that happens during the algorithm. So in particular, let me see if I can find an example. Let me find an example of this. But there were I saw a bunch of examples like at least one swap happens on every pass, on every iteration. Okay. So this is saying something about what happens during that. Okay. So on the one hand, I mean, it's true, at least one swap does happen every pass except for the last one. But on the other hand, usually an invariant is described as a relationship between variables. If an invariant says something about the state of the array, says something about the state of the algorithm. So usually you want to describe your invariant in terms of the state, not in terms of what has happened. Okay. Though again, there are times when talking about what's happened is important. I don't want to claim that's never important, but that's not usually how we talk about invariants. Okay, and then a bunch of people talked about the invariant in terms of which part of the array is sorted, or which part of the array has what size elements in it. And that is how you want to talk about an invariant. It's saying something about the array and the state of the array. Okay, if you look, let's look at what happens. Let's see if we can think about this invariant a little bit more. What happens in iteration 1? The maximum element in this whole array might be 10, for example. And at the end of this iteration, the 10 is going to swap, and then it's going to swap, and then it's going to swap and swap. And eventually, by the end of the iteration, it's going to end up over here at the far right side of the array. So after iteration 1, the maximum element is going to be at the end of the array. Right? So what happens after iteration 2? After iteration 2, the second largest element will be at the end of the array. Okay. And in general, at the end of iteration j, what we're going to know is that the j biggest items are going to be in the final j positions of the array. Okay. Now, I could have just said that the biggest j items are in the final j positions of the array. Right? Without that extra part, that is still a correct invariant, but you'll notice it's not quite as useful an invariant, right? Without this part that I crossed out, if the invariant was just at the end of iteration j, the biggest j items are in the final j positions, that wouldn't actually tell us that the array was sorted. We get to the end, we get to n iterations, and what do we know? We know that n items are all in the last n slots of the array. That doesn't tell us anything at all. So the real invariant is actually stronger and includes the fact that they are correctly sorted in the final j positions. So someone pointed out in the chat, yes, because if all I knew was that the last 3 elements were the 3 biggest elements, it could be that it was like 9, 8, 10 or something. Maybe some later iteration messed with the end of the array and caused trouble. So this is about how do you choose a good invariant, right? And again, yes, it's related to how do we prove things like this by induction. Okay, great. Okay, so given this invariant, then it becomes immediately clear that if this invariant is true, then after n iterations, the whole array is sorted. This is what we want from an invariant, right? What we want from an invariant is the fact that it tells us that when we're done with all of our iterations, then we have the final goal, which is the array is sorted. That's what makes this a good invariant. It's about the state, and it tells us what we need to prove the algorithm correct. And it even tells us the running time. It tells us that in the worst case, it's going to take at most n iterations. So we get a lot of things from this one invariant. Okay, worst case n iterations. And so that means the running time is going to be order n squared. Okay, good. So BubbleSort is worst case order n squared. Good enough. That is all I have to say about BubbleSort. Let me just check my random questions board to see if anything new has shown up before we go on. There's a question about why is the best case order n? Let me go back a step. Oop, what just happened? Not that. Why is the best case order n? Well, think about what happens if you run BubbleSort on an already sorted array. I claim that just one pass through the array, you discover it's sorted and you are done. Okay, so go back and try to run BubbleSort on a sorted array and see what happens. Okay. Can I repeat what makes a good invariant? So in particular, there are a couple of things that we want from a good invariant. So one of them is it should be about the state. Right? A good invariant is a relationship between the state of things. The second thing we want from it is that it's useful. Now, this is more subjective, obviously. What do I mean by useful? That's going to depend on what you're trying to do, obviously. But in this case, useful tells us something that at the end, whatever the end is, after n iterations, so this might mean like n iterations of our sorting algorithm, the state is such that we get a correct answer. We get correct answer. So if you think about the BubbleSort invariant I gave, it tells us that after n iterations, the array is sorted. That's great. That's a very useful invariant. We won't always get invariants that are quite that good, but that's sort of what you hope for. That's the best case. Okay. I hope that helps. Let's see, does the worst case for BubbleSort occur when the array is in reverse order? That's certainly one case that will give n squared if the array is in reverse order. Okay. Let's see, what else do we have here? Is BubbleSort applicable in real life? I think I mentioned before, BubbleSort is very rarely actually the right sorting algorithm to use. On the other hand, basically every other sorting algorithm we talk about does have its uses. So SelectionSort, InsertionSort, MergeSort, QuickSort, all of these actually have real situations in which they are the best algorithm to use. So BubbleSort is an outlier. It really is just a didactic example. But everything else we're talking about matters. Okay. Okay, good. Yeah, BubbleSort doesn't really matter, and shell sort, it's not clear if it matters. That's one reason we're not doing shell sort. Though it is interesting from a theoretical perspective. Okay, let us go on to SelectionSort. Okay, SelectionSort, here we go. Here is SelectionSort. So someone asked, by the way, what do I mean by this arrow? This is an assignment operator here. This is just notation to mean for j, as j goes from 1 to n minus 1. Okay. Yes, throughout this class, I'm going to use pseudocode rather than always writing strict Java code, because this would take a lot more Java code to express what is otherwise, I think, a fairly clear set of 3 lines. Okay, so how does SelectionSort work? In SelectionSort, we're going to imagine that we have a sorted prefix. So over here, over here, we have a sorted prefix of our array. Okay, we've already sorted the items from 1 to 6. Good. And now we want, what's the next thing to do? We want to look for the next smallest item. Okay, we want to look for item number 7. Okay, there's item number 7. So we find item number 7, which is the minimum element in this suffix. There we go. We find the minimum item in this suffix. We take that item and we're going to swap it into place. Okay. Someone says in the chat, I should write code in Ada instead. Interesting suggestion. I'll ponder that. Okay, so here's an example of selection sort. Again, we have our nice simple array. We start out with our prefix of size 1. Well, that's already fine. That's already, well, the first thing we have to do here, sorry, our prefix of size 0. Okay, the first thing we have to do is find the smallest item in the array. So we find the smallest item in the array. That's going to be item 2. There it is. We found it. We found item 2, and we're going to swap item 2 to the beginning. I see a question in the chat. Is heap sort a variant of selection sort? Not really. We will get to heap sort later this semester, but not today. Okay, so now we've done one iteration. We've chosen item 2 and we've swapped it with 8 and put item 2 in the beginning. Now we need to find the minimum item in this suffix of the array. We find item 3. There's our minimum item. What do? We're now going to swap item 3 and item 8. There we go. We put item 3 close to the beginning. We put item 8 close to the end. Done. Next iteration, we find the minimum item here. The minimum item is 4. We now swap item 4 with item 4. Great, done. Now again, we find the minimum item at 6, and we swap it into place. We find the minimum item 8, we swap it into place. We find the minimum item 9, we leave it where it is, and we are done. We have a sorted array. Okay, so the nice thing about selection sort is it just very cleanly goes through, picks an item, and swaps it into place. Okay, each item gets swapped only once. That's great. The item is swapped into place, and it is good. Okay. I see a question, why am I doing item index 1 instead of index 0? Because it doesn't matter. As long as we are consistent with our indexing, everything is okay. We only get into problems if we switch between whether we're 0 or 1 indexed. Okay. Okay, over to Archipelago. Oop, it's not open yet, the question. In this case, what is the worst case running time for a selection sort? Let's go over to Archipelago and see. So there's a question about the selection sort. It directly swaps element with another, but for BubbleSort, they only swap with neighbors. So yes, so the difference is selection sort finds the right item and swaps it in place, while BubbleSort only swaps adjacent items in the list. So this is much better in that it just swaps the item into the right place and then you're done with it forever. That's great. That's the great thing about selection sort. Okay. Good. And as I said, there are cases where selection sort is the right algorithm to use. I won't talk about that today, but I'll leave that as something to puzzle out. When would you use selection sort? Okay, good. So people seem like Archipelago is working. That's great. I have some answers. The answer is going to be n squared. So again, this is an n squared running time algorithm. But again, just like before, let's think through a little more carefully how we could show that. Okay, so here was our algorithm. Well, the first thing we're going to have to think about is there are basically two interesting steps to this algorithm: finding the minimum element and doing the swap. Okay, well, finding the minimum element during iteration j is going to take time n minus j. Think about it. If we have items 1 to j minus 1 here, how long will it take to scan the rest of this array? Well, it'll take time n minus j. Okay. So it's n minus j for this. We're going to assume that we can do the swap in order one time. Someone in the chat points out n minus j plus 1. Possibly we have an off by 1 error. It's true. This is the advantage of asymptotic notation, is I can ignore the plus 1. It won't matter. But that's a good catch. Okay, great. And then the swap, right? So what is the total running time then? So the first iteration is going to be n, the second is going to be n minus 1, the third is going to be n minus 2, the fourth is going to be n minus 3, and so on, right? This is finding the smallest item, the second smallest, the third smallest, the fourth smallest. So yes, this certainly looks a lot like n minus j plus 1, doesn't it? Okay, what's that going to be? N times n plus 1 over 2, which is theta n squared. Okay, great. So that's the running time of selection sort. Here's another question. What is the best case running time for selection sort? We don't often care about best case running time, but let's think about this for a sec here. What is the best you could hope for? Please answer on Archipelago. I am seeing a close tie between two answers, so you better get your vote in. Okay. Good. Let's go on then. So best case running time. This is interesting. Sorry, I was also just checking the random questions to see if there's anything I should stop and add and address. Okay, so we do have a winner. We do have a winner here of n squared by a vote of like 300 to 200 or so. We have n squared as the winner. And so here is the interesting thing. The interesting thing is that selection sort is no faster even in the best case. So why is that? Let's think about for a sec what happens when you run selection sort. When I run selection sort, I have, like, even if the array is sorted, let's imagine this array is perfectly sorted. I still have to, if I find whatever item I find here, I still have to check the rest of the suffix to see if there's anything smaller. There could be, right? I mean, this case here is sort of a silly one because I have integers from 1 to n. If I knew I had only the integers from 1 to n, fine. But you might have the entire English language dictionary here. And if you have the entire English language dictionary, the only way to know that the next word that you have is the smallest is to scan this entire suffix, even if we don't learn anything new. So no matter what happens, we have to pay the n minus j plus 1 for this line of code, even if the array is already sorted. And so it's going to take n squared no matter what. And so we might notate that as the running time of this algorithm is omega of n squared. Okay, it's going to be at least n squared, even in the best case. Okay. So there's a question of, does omega mean best case? No, omega doesn't necessarily mean best case. Omega refers to something, a function being at least something. In this case, it's going to be at least n squared. Okay. But the algorithm, you would say this algorithm is theta of n squared. Yes, this algorithm has theta of n squared running time. It runs in n squared for every single execution. Okay. Oh yeah, there's another typo. Find the minimum here. Find the minimum element in this range. There we go. That's more clear, I think, anyways. Oh, whatever. Anyways. Okay, next question. What is a good loop invariant for selection sort? Where is it? There it is. What is a good loop invariant for selection sort? Just like for BubbleSort, think about for a sec how this works and tell me what you think is a good way to think about the way selection sort works. Oh, wait, no, I opened the wrong question. That is not a selection sort. Wait, I don't have a question on Archipelago for selection. Oh, there it is. Ha, there's the selection sort loop invariant question. Okay, sorry about that. I will give you a minute or two to think about a good invariant. If you can't see it, all I can suggest is reloading it. For some reason, you seem to be having trouble with Archipelago today. I don't know why. We've been having good luck with Archipelago today, but I seem to have confused it. Okay. Okay, it seems like at least a few people have been able to put in answers. Maybe half of you, I'm not sure. But let's see what people wrote. So for example, I'm seeing invariants that say things like a new list is the new list created is sorted. So again, new list created is sorted is probably not a great invariant here because we don't know, like, I mean, it's true at the end that we have a sorted list, but it's not really a loop invariant. It's not something that's true at the end of each iteration, okay? I see some people writing things like everything on the left of J is always sorted, okay? So everything over here is already sorted. So this is a true invariant in the sense that everything in the prefix is already sorted, though it doesn't quite capture everything you might want. It is enough, though, in order to prove that the algorithm works, right? If I know that everything to the left of J is sorted, once I get to the end, I'll know that everything is still sorted, okay? But in fact, there's a slightly stronger invariant that's also true, beyond just the prefix being sorted, and that's that at the end of iteration J, the smallest J items are correctly sorted in the first J positions of the array. Okay, good. So this is something that you'll notice is true from the algorithm by construction. In each iteration, we add the next biggest element, and so the prefix will always contain the smallest items and a sorted list. Okay. Something to notice here is that the weaker invariant, the fact that the prefix is sorted, is good enough to show the algorithm works, but the stronger invariant might be useful, for example, to use during induction to show that everything is actually working the way it's supposed to. Okay, the stronger one here is more useful for an inductive argument, even though the weaker one is enough for getting to the end. I see some random stuff going through the chat right now. Can we please keep the chat sort of on topic here and not to random jokes? To the extent that you would like to have random joking chat, can you go find a different chat that isn't the Zoom chat for this? Thanks. Okay, good. So that is SelectionSort. Great. One sec, I saw a few random questions from the random question list that I wanted to answer on the way. One sec, let me figure out what those are. Are we going to learn heap sort? Yes, eventually. What is the most efficient sorting algorithm? We'll get there. What is the point of invariants? Good. The point of invariants is that they help you to understand how the algorithm is working, and they help you to show that it is actually working. If you understand the invariants, it's much easier to see the algorithm is doing what you want. If you don't have any invariants, it's very hard to know, is this actually doing what I think it's doing? For a simple algorithm like we've been seeing, maybe it's obvious to you, right? Maybe it's sort of obvious as you're going through that that the algorithm is doing what you think it's doing. But as the algorithms get more complicated, we're going to discover that you need to identify what's really happening if you want to make sure it's correct. Okay, so I suppose for these simple examples, hopefully these give you some insight as to why it might help, and keep this question in mind as we get to more complicated algorithms. Okay. I think there was at least one more question I wanted to answer. Where did it go? Don't know. Okay, I'll come back to it if I can find it later. Okay, we have done 2 sorting algorithms. We're also about an hour through class. So I think now is a good time to take a break, which also means I want to jump ahead to the puzzle of the week, which unfortunately is not here. So I'm going to have to try to find it. Where can I find it? Where can I find it? Should be somewhere around here, no? Here we go, puzzle of the week. Okay, here is our puzzle of the week that you can think about during the break. Gambling for profit. We haven't done much probability yet this semester, but we're going to be talking more about probability in the coming week or so as we get to quicksort. So as a warm up for probability, here is a confusing probability question. So we have Alice and Bob, and they're going to try some gambling. Okay, each begins with $100. They're gonna each bet $1 each time. Maybe they're playing roulette here, or maybe for now we can just think of them playing with some coin flipping game. Okay, and so every time on each coin flip, they're gonna bet $1. Alice, she chose the right table to gamble at in the casino. She's betting heads every single time, and the coin is biased and is going to come up heads with probability 51% each time. Okay, so every bet has a 51% chance of winning. Alice wins $1 with 51% and loses $1 with 49%. Bob, on the other hand, was not quite so smart. Bob chose a different table at the casino. His bets are only winning with 49% probability. So he's betting on tails every time, for example. Tails is coming up only 49% of the time. So each of his bets has a 49% chance of winning. With 49% of the time, he wins $1. 51% of the time, he loses $1. Okay. So alas, it turns out at the end of the day, despite the good odds, both Alice and Bob end up losing all their money. They're gambling at 2 different tables, but at the end of the day, they lose all their money. Tough luck for them. That's why you always be careful going to gamble. So here is the question. Who is more likely to go bankrupt first, Alice or Bob? Okay, so that's the question. Some hints I will give in case you're interested. Bayes' rule, okay. I also did a little bit of the calculation for you just in case you haven't done random walks yet before. It turns out that Alice will eventually go bankrupt if she plays forever with probability 0.49 divided by 0.51 to the 100th power. This is the probability that Alice eventually goes bankrupt if she plays forever. Okay, and the third thing I'll tell you is, the third hint I'll give you here is that for every sequence where Alice loses, you can construct an inverted sequence, flipping all the heads and tails, where Bob loses. And I will stop there. Those are my hints for the day. I'll let you think about who is going to lose all their money first. Okay, let's take a 7-minute break, stretch your legs, stretch your eyes, get some water, think about the puzzle of the week, and we'll be back in 7 minutes. Okay, let's get started again. So we have lots to do and not a lot of time, so we're going to keep on going. Okay. Let me, in terms of this puzzle of the week, let me say one or two other things, which is sort of how would I approach this problem in general. The first thing, I guess there are two things that I would think about if I were curious about this question. One thing I might try to do is I might try to actually simulate it, right? This seems like a pretty easy thing to simulate. So I might try to actually simulate it and see what happened, okay? On the other hand, there are two problems you're going to run into if you try to simulate this. One problem you're going to find is that 51% and 49% are close enough probabilities that that it might be hard to see the difference, right? It might be hard to actually see what's happening. Okay. The other problem that you might have if you simulate it is that, well, most of the time Alice is not going to go bankrupt, right? It's pretty unlikely that Alice goes bankrupt. I mean, what is 0.49 divided by 0.51 to the 100? I don't know, I haven't actually worked it out, but my guess is a pretty unlikely number, okay? So if I were trying to simulate this, I'd probably try to fix both of those things. I would probably try to say, gee, what happens if Alice wins not 51% of the time? What if Alice wins 75% of the time? Okay, but then my other problem becomes even worse. Okay, my other problem becomes even worse. So I might say, what if Alice starts not with $100, but with $5? That makes it a lot more likely that Alice will go bankrupt. So basically, I would try to accentuate the extremes of the problem to make it more clear what was happening. I see a question saying, what distribution does the event follow? The event is just a coin flip that comes up heads with probability 51%, tails with probability 49%. Anyways, I think that's all I'm going to say about this for now. Again, we can talk about this some more on the forum. I think it's sort of an amazing thing. Okay. Good. Let me see if I can find my way back to wherever we were before. Where were we before? Somewhere back here, maybe. Let's see. We were past this point. This is exactly where we were. Excellent. So we've done BubbleSort. We've done SelectionSort. On to our third sorting algorithm of the day, InsertionSort. Okay. Here is sorting algorithm number 3. How does this work? So InsertionSort is a little bit like SelectionSort. Again, we have a sorted prefix. Okay. But this time, we're not going to waste our time searching for the minimum item. We're just going to take whatever the next item is. So this one here, for example. Okay. And we're going to insert it into the right place in the prefix. Okay. We'll just bubble it backwards through the prefix until it finds the right place. So this is better because we don't have to waste our time searching this entire suffix. We just have to we always take the next element. Okay. Great. So here's an example. Here's our sorted prefix. We take J and we move this item backwards until it arrives in the right place. Okay. Here is some pseudocode for that, or even, yes, some pseudocode that that looks a little bit more like real code. Basically, we're going through, looping through everything. We take the next item, and this is moving it backwards in the array until we get to the right place. Okay. There was a question on the random questions, by the way, about, I think in jest, asking, how do I learn to write pseudocode? Is there an API for that? And I'm guessing because of the question about an API, that this was a joke. It is true that writing good pseudocode is important in the sense of it is good to learn how to express your algorithms clearly and efficiently, okay, in a way that is easy to understand. Okay, good enough. So let me go through an example of insertion sort. So the first iteration we go through, we have the first item. There's nothing to do with the first item. Good enough. Okay. Next, we move on to the next item. Now we have to insert this second item into this prefix in the right place. Well, where is the right place in the prefix? The right place in the prefix that comes before 8. So we insert it there. Now we're going to take our next item and insert it into this prefix. Where does it go in this prefix? It goes over there between the 2 and the 8. So we just swap it. We just swap it backwards and it is good. Next, we need to take the 9 and insert it into the prefix. Where does 9 go in the prefix? It goes right where it is, nothing to do. Next, this item here, 3, we have to insert it into the prefix. Where does it go? It goes over there. So we're going to move it back. We're going to sort of bubble it back until it gets into the right place. There we go. Now the 3 is in the right place. And now how about the 6? Same thing. We insert it into the right place over there. And we are done. We have a sorted list. That is insertion sort. It's called insertion sort because you are inserting each item directly into the right place in the prefix. Okay, so here we go. Our usual questions. I have to open the question archipelago. Wait, insertion sort running time. Yes. What is the worst case running time for insertion sort? Go on over to archipelago and tell me the answer. We have a fairly unanimous decision this time. Almost everyone tells me that it is n squared. Okay, and almost everyone is correct. I think you are seeing a pattern here now. We've seen a lot of n squared algorithms today. Okay, so how to think about this? Let's go through the analysis of this. The key question we have to ask is how far does the key need to be moved? Right? That's sort of the key question, because finding the next key, this part here is easy, right? This part here is easy. That's just taking the next item. So all the cost of the algorithm is really this moving it backwards part, this part here, right? So that's the question then is, so how far do we have to move things? Okay, well, the easiest thing we can do is we can say, what's the farthest we could have to move something? What is the maximum? What is the worst case? Well, clearly the worst case is going to be J, right? The worst case is going to be J. Clearly, we do not have to move the item more than distance J on the Jth iteration. Let's go back to the previous slide and see. Clearly, the farthest we might have to move this is all the way back to the beginning. Okay. Great. Well, that means that for the first iteration, the farthest we have to move it is 1. For the second iteration, the farthest we have to move it is 2. For the third iteration, the farthest we have to move it is 3. We sum all of these things up from 1 to n. This is again n times n plus 1 over 2, which is theta of n squared. Okay, good. So the running time of insertion sort is going to be order n squared. Okay. By the way, at this point, someone often asks the question. I have to check if it's shown up on my random questions board yet. Maybe it has. I think there is the question there. They say, wait a sec, why do you have to move things back so slowly? Why can't I just swap this item back there in order 1 time, and then I'd have a linear time algorithm? It would only be order n. Right, I could just do a binary search on this prefix, binary search, find the place that it goes and do a single swap operation, and then it would be a lot faster, right? The problem with that is because we have to insert the item into this prefix, which is going to require moving everything else backwards, right? So we're still going to have the same cost of moving everything backwards. We can't help that. As long as we're storing everything here in an array, there's going to, on iteration j, be a worst case cost of theta of j to move this item into place. Okay, but this immediately raises, and again, this is now, I'm not going to go into detail here, but this immediately raises the possibility of, gee, we could come up with a faster insertion sort if we could insert things faster into arrays. What if, for example, we left some gaps in our array, right? Imagine that we had left some empty space here in the array instead of keeping it tightly packed. Maybe then we could have inserted it faster. Possible. What if we were not using an array, but some other sort of data structure to store things? Again, possible. So there actually are interesting implementations of insertion sort that are faster because they don't use arrays. One of them, in fact, is called library sort, but I will leave that for another discussion today. For our purposes for this class, insertion sort involves an array like this. Okay. Someone says something about creating a new array. Creating a new array tends to be expensive because you have to copy things over. You'd still spend that same cost in creating the new array. Okay, but again, there are things you can do. There are interesting solutions to this problem that can lead to things that look like insertion sort but are faster. So that, again, we can discuss this later on the forum. It's a fascinating area, but for today, insertion sort is going to be n squared. There's a question, what's the difference between selection sort and insertion sort? Ah, good. Let's talk about that. And here's how I want to talk about that. I want to talk about that in terms of the invariant. Maybe this is a good illustration. Insertion sort loop invariant. I just opened the question on Archipelago. Maybe this is a good illustration, in fact, of how an invariant helps us to understand what an algorithm does. So let's go put your favorite invariant for insertion sort into Archipelago, and then we will talk about that. And in doing so, I hope we will distinguish selection sort from insertion sort. And yes, I'm sorry if selection sort, insertion sort got confused. I'm sorry. I don't know how to reset a question on Archipelago right now, so we're stuck with the way it is. That's okay. You can write down the invariant on a piece of paper in front of you for the same purpose. Oh, I can't see it then, I suppose. Okay, I think people are getting the hang of this invariant thing because I'm seeing lots of correct invariants here. In particular, so I'm going to go on because I'm seeing so many correct answers that I'm going to go on here. In particular, the key invariant here is that at the end of iteration j, the first j items in the array are in sorted order, right? So what we know is that we have a sorted prefix that we are maintaining at all times, and then we insert the next item into it. That is a terrible picture. Here is this. We insert this item into it, and once we've done the insertion properly, we again have a sorted prefix. Okay, so the key invariant here is that the prefix is sorted. How does that differ from selection sort? Remember, we talked about two possible invariants for selection sort. The weaker one was also just that the prefix was sorted. Fine. But we had a stronger invariant as well. And the stronger invariant for selection sort said that the prefix was sorted. This is for selection sort. Said the prefix was sorted and they were the smallest j elements. Okay. Notice that that isn't true here, right? So unlike for selection sort, there is no guarantee that the prefix contains the smallest elements. The prefix can contain the largest j elements for all that we know, right? It could be that it has lots of big elements in the prefix. That's fine. That's well and good. In fact, here's a fun experiment. Come up with an array where at all times throughout the execution of insertion sort, the first j elements are the largest j elements in the array. You can come up with an input where that is going to be true. That will never be true for selection sort. Okay. After the first iteration of selection sort, the smallest element is in position 1. Okay. So this is so the question of why selection sort and insertion sort are different. First of all, this is important because you have to think how they operate differently. One is inserting the next item. The other is searching for the smallest item. And the second is to think about it in terms of invariance. Okay, to think about it in terms of selection sort has a stronger invariant that the smallest items are always in the front, where insertion sort allows for a weaker invariant. Okay, good. And this also means that in practice, often insertion sort is going to be faster, by the way. Insertion sort tends to be a fairly fast algorithm among this class of n-squared algorithms that we're talking about. Okay, good. I say archipelago is open. What question was I asking here? I wonder. I guess I'm gonna skip the archipelago question here. I guess I was asking about best case and worst case performance for insertion sort, but we don't have a lot of time, so I'm gonna go on. So one thing to think about is sort of what inputs give you good performance, what inputs give you bad performance. And if you think about it a little bit, what you'll realize after a few moments is that if the array is already sorted from 1 to n, then insertion sort is going to be super fast. It just scans through the whole array once, gets to the end, and it's done. Order n time, it is very fast in the already sorted case. Of course, the worst case for insertion sort is the inverse sorted case, sorted from 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. If you think about what insertion sort does on that, every time it has to move the next item all the way to the beginning. So for example, imagine that we have sorted this prefix and item 6 comes along, it has to be moved all the way to the beginning. And then this item here has to be moved to the beginning. And then this item gets moved to the beginning. And so every single time you're taking the maximum worst time. Okay, good. All right, very fast, very slow. Here's something interesting. As I said, we're not going to talk a lot about average case analysis, excuse me. But it's interesting to think about sometimes. How is insertion sort going to work on a randomly chosen permutation? Imagine that I randomly scramble the entire array. Do you think it's going to be any faster than in the worst case? Okay. This is an interesting question. I claim it will not actually be that much faster, that random inputs are actually not very good for insertion sort. Let's think about that. Here's the key claim. I claim that on average, if you choose a random input, the key in position J will need to move about J over 2 slots backwards in expectation. Let's think about why that is. Here is sort of an example. So let's imagine I have a sorted prefix. Here it is. And I ask, how far is item 7 likely to have to move? This is a random input. It turns out that if you think about this sum, you will realize that 7 is equally likely to go anywhere in this prefix. It's equally likely to go at the beginning. It's equally likely to go at the end. Because it's a random array, 7 is equally likely to go in each of those positions. And so because it's equally likely to go in each of those positions, on average, in expectation, it's going to move back J over 2 slots. Okay? It's going to move back to somewhere around the middle, on average. Okay, so what that means then is that you sum up the J over 2s, and you will end up with theta n squared as your average case cost. Okay, great. So that is it for insertion sort for today. Okay. What if it is given that the elements are all non-negative? That doesn't actually change much. It's still going to be J over 2 on average. And in fact, in general, the values of the elements don't matter here because all we're doing is comparing them. So all that matters is that we can compare elements and figure out which is bigger. Yeah. Obviously, this would not be true if all the elements were the same. If I asked you for insertion sort, what is the running time on an array where all the elements are identical? You will, I hope, quickly realize that it's going to be much faster. Okay. Good. Let me check the random questions and see if there's anything interesting there before I go on. Random questions, random questions. Okay. I don't see anything interesting on the random questions right now, so I'm going to go on. Okay, good. So we've talked about BubbleSort, SelectionSort, and InsertionSort. We're going to get to merge sort at some point. Maybe that's going to wait till Wednesday. But I want to talk about a few other properties of sorting algorithms. Okay. Before we get there, interesting. I guess I had this as an archipelago question, but I'm not going to pause and let you answer. But I will leave this as another puzzle you can think about. Try to invent the slowest sorting algorithm you can think of. And I will give you a hint, it is not BubbleSort. You can definitely do slower than BubbleSort. Okay, and the hint I will give you is that recursion can be a powerful source of slowness. Okay, anyways, I will leave that as something fun to input on Archipelago, and or we can talk about later on the forum. But let me go on for now. It's a fun challenge. Think of the slowest thing, but of course it has to always be correct and it has to always terminate. If your algorithm doesn't actually sort, that doesn't count. You have to actually do the sorting. Okay, and no, just sleeping for 1,000 somethings is definitely not going to do it for any notion of slowness. That will not be very slow in practice compared to some of the other algorithms we can come up with. Okay, good. So I want to talk about the properties of sorting algorithms. Okay, so we've already talked about the worst case time complexity of an algorithm. Good. So we know that all the algorithms we've talked about so far have worst case order n squared running time. Okay. The other thing that we've already talked about is how well does the algorithm already perform on a sorted list, right? So for example, BubbleSort and InsertionSort are both fast on a sorted list, while SelectionSort still runs in n squared time on a sorted list. Okay, great. Here's an interesting question. What if your list is almost sorted, right? So for example, here is an array where there's only one item out of place, right? You just swapped the 6 and the 7. How expensive is it to sort this array? Well, we already know SelectionSort is still going to be n squared. Okay. At the same time, we would expect things like BubbleSort and InsertionSort to be better. Okay, BubbleSort and InsertionSort will be fast here. SelectionSort will still be slow. Okay. Here's another question. Maybe another challenge for the day. You might want to try to find a permutation where BubbleSort is slow and InsertionSort is fast, or explain why no such sequence exists. Can we differentiate BubbleSort and InsertionSort based on some interesting permutation? Okay, this might be useful for your problem set, right? So we need something where BubbleSort's going to be slow and InsertionSort's going to be fast, or you need to tell me that you can't do that because whenever InsertionSort is fast, that means there aren't very many things to swap, and that means BubbleSort will also be fast. I don't know. You'll have to. You can make the argument. Okay. I see a question about won't the number of swaps be the same? I'm not sure if this is in the context of something else, but remember, we are not just counting the number of swaps, we're counting the total running time of the algorithm, right? Each algorithm has some total running time, and that's what we're talking about. Okay, so sort of the moral of the story here is that different sorting algorithms have different inputs they are good or bad on. So all order n squared algorithms are not the same. Okay, great. Here's something else we can talk about. We can talk about space complexity. How much space does a sorting algorithm need? In particular, all the algorithms we've talked about need order n space in the worst case. And in fact, any sorting algorithm that needs more than linear space is really fairly useless as sorting algorithms go. We don't want to be using n squared or even n log n space to sort. Almost any reasonable sorting algorithm takes order n space. Okay. An in-place sorting algorithm is even stronger. An in-place sorting algorithm doesn't use any extra space. It just uses the n elements in the array and then maybe some order 1 extra space. Okay, so all the manipulation has to happen in the array. So there's an input array. Here's our input. Okay, and here's our input. And there's only order 1 extra space needed if it's in place. So there's a question in the chat of, do we count input space in the space complexity? And I think this is going to depend on the question. We have to be very clear when we talk about space complexity, if we are talking about sort of total space, including input, or total extra space. And I will try to always be clear about this. So when I talk about in-place sorting algorithms, I'm talking about the extra space that you need aside from the input. Okay, good. So far, all the sorting algorithms we've seen are in place. They all need only a small amount of extra space to manage the comparisons and so on. They all do everything in the array itself. Okay. There are occasionally some subtle issues that arise when you want to count up space complexity, because space is not a fixed thing. If you've taken 2100, you know that there's space being allocated and deallocated. If you studied C, you know that you can allocate and deallocate space. If you study Java more, you know there's garbage collection going on. So if you care about sort of practical running systems, space can be hard to count. For the purpose of this class, I don't want to get into all of that. And so we are just going to count the total space that is ever allocated. If that space has been allocated, then it counts. Okay, we're not going to worry about something more subtle like the maximum space allocated at one time. We're not going to worry about garbage collection. We're not going to worry about stack frames. All of these are very valid and good points. And as I said, it's sort of a fun exercise is come up with some examples where the assumptions I'm making here are clearly and obviously wrong. This is the wrong way to measure space. I bet you can come up with a couple examples. Okay, but for the purpose of this class, if we ever use the space, it counts. Okay, great. Okay, let's talk about stability. This is another interesting property of a sorting algorithm. Yes, in-place algorithms only consume order 1 extra space. Yes. Okay, let's talk about the stability of a sorting algorithm. So what happens with repeated elements? Remember I said that repeated elements are an interesting thing to think about in a sorting algorithm. So let's imagine we have an array. Here are the of key value pairs. So the key is the thing that we want to sort by, and the value is sort of the extra thing that comes along with it. So the key might be your student ID, and the value might be your name, right? This is a reasonable thing. And databases often contain key value pairs. We're going to talk a lot about key value pairs when we think about storing data, okay? And of course, it's entirely reasonable that in your database of key value pairs, you might have two things with the same key. So here's an example. We have the key 5 that has the value that has two different values associated with it, C and D. Okay, that's fine. So now the question becomes, what happens when I sort this array? Right? No problem, I can still sort this array. Here we go. I sorted the array, and now it is perfectly well sorted by key, right? 1, 2, 3, 4, 5, 5, 6, 7, 8, 9. Good. But you'll notice what happened when I ran my sorting algorithm. It used to be beforehand that C came before D. Now, after the sorting, C comes after D. Thus, we say this is not a stable sorting algorithm. Okay. If you want the algorithm to be stable, you want it to keep the same order if the keys are the same. So this is stable. This is unstable. Okay. Stable. Okay. Good. So does that make sense? Okay, so then here's a question. Give me a sec to open the question on Archipelago. Here we go. Which of these algorithms do you think are stable? And I believe that you can choose all that apply. Yes, select all the answers that are correct. Okay, I'll give you 10 more seconds to input something on Archipelago. Okay, excellent. Let us go on. Let's think about whether these are stable. The first thing, I think most of you identified that BubbleSort is not stable. Okay, every time we take a random permutation, the odds that we end up swapping things that we didn't want to swap are pretty high, right? We choose a new random permutation, we're going to swap things. So BubbleSort is not stable. I'm sorry. Luckily, I don't think you were planning to use BubbleSort. Let's talk about BubbleSort. BubbleSort is stable, right? In BubbleSort, you can be careful in your implementation and only swap elements that are different. So if I'm coming along and doing my BubbleSort, here it is, and I have to compare two elements and they have the same key, well, don't swap them. If you don't swap them, then your BubbleSort will be stable. If you implement your BubbleSort badly and do swap them, then it won't, okay? But a correct implementation will be stable. Okay. Let's think about SelectionSort. Alas, despite what 275 people think, SelectionSort is not stable. By the way, I'm announcing the number of people who got it wrong, not to embarrass anyone, but quite the opposite, to indicate that it is totally fine to get these questions wrong. Lots of people do. There is no expectation that you will get every question right. So 275 people thought that SelectionSort was stable, but it is not. Okay, let's think about why SelectionSort is not stable. Let's imagine that we're coming along here and we're trying to find the next item that goes in order. So here is the suffix of our array, okay? And we search the suffix for the smallest element, and here it is. We found it. We found item 7. That's the smallest item. Now, what do? We swap item 7 with this item here, right? That's the next step in SelectionSort. Unfortunately, there was another key that had the same value, this one here, another 8, that was in between. And because it was in between, alas, we have now switched the order of the 8s. Here we go. Before, this 8 came before this one, and afterwards, this 8 comes before this one. So we have flipped the order of the 8s, and SelectionSort is not stable. Okay, great. So SelectionSort you have to be careful with. It does not have to, it may not be a stable algorithm. If you want to make it stable, you'd have to be a lot more careful in your implementation. Okay, great. How about InsertionSort? InsertionSort, by contrast, can be stable as long as you are careful not to swap identical elements. So here, of course, is the key to implementing stable InsertionSort. When you are deciding whether to bubble your item back farther, you better check, is it greater than or is it equal? And if it's equal, then stop swapping. So again, here is your sorted prefix. We have some item 7 back here. We have some 7 back here. We are bubbling this 7 backwards. Boop, boop, boop. Don't swap the two 7s. Keep them in the same order. Then your InsertionSort is stable. And again, a correctly implemented InsertionSort will be stable. Okay, great. So this is where we are at. We've talked about BubbleSort, SelectionSort, and InsertionSort. They're all n-squared algorithms. Okay, there's a question in the chat. So stable means can be stable, and unstable means never can be stable? No. So in general, I want to talk about stable or unstable with respect to a given implementation of the algorithm, with a given algorithm, right? So in particular, when I tell you that something is unstable, I don't want to have an argument that, well, you could have implemented a different algorithm that would have been stable. Often that's true. And conversely, if I tell you an algorithm is stable, yes, you might be able to come up with a version of it, a different algorithm that is unstable. But again, that's not really the point. We want to talk about stable or unstable with respect to a given algorithm. And so here, for example, this is how InsertionSort is implemented. InsertionSort does not swap equivalent items, and so InsertionSort is stable. Okay. It's a good question though, because we should be clear that we can only talk about these things with respect to a given algorithm. I'm not saying anything about all algorithms either way. Okay, so we've talked about 3 different algorithms. We've talked about time. We've talked about space. We've talked about stability. It's 5:45, and so we're about out of time. I don't want to start something new then, because we are running out of time. Next week, on Wednesday, we're going to keep going and talk about merge sort, right? Merge sort is a sort of canonical divide and conquer algorithm where we're dividing a problem into smaller subproblems, recursively solving them and recombining it. So this is what we'll talk about next time, is merge sort and divide and conquer, and the divide and conquer paradigm. Okay, let me see if there are any last questions to answer. Can we find a specific implementation for selection sort for it to be stable? I mean, if you spend enough time checking things carefully, you might be able to, yes, but you will have to be careful. And again, that's not how selection sort tends to be implemented. Can I show the best, average, and worst case for BubbleSort again? So we didn't actually go over the average case for BubbleSort. For BubbleSort, we saw that the best case for BubbleSort was order n, and the worst case was n squared. It turns out the average case for BubbleSort will also be n squared, but I don't think we actually showed that. Okay. Let's see. Let me see if there are any random questions to answer before we call it a day. Let me check the random questions list. There's a question, must we always use the most efficient sorting algorithm? So no, in fact, sometimes you'll want to use a sorting algorithm that is less efficient, but has a property that you want. So maybe you want an algorithm that is in place and stable, even though it's slower. So in general, you will want to think about the properties you want from the algorithm. Sometimes speed is most important. Sometimes another property will be more important. And this especially gets interesting when you talk about things like databases, where you might care about concurrency. You might care about the locking paradigms. You might care about cache efficiency. There are a lot of interesting properties that you might be interested in beyond just the pure asymptotic speed. But it is true that often, and especially in this class, we're going to be trying to find the asymptotically fastest algorithms. Okay. There's a question in random questions. How would you prove that these loop invariants are true? And in general, the proofs here would be an inductive argument. You want to show that if the loop invariant was true before the loop, then it's also true after the loop. And for the examples we gave, that's a pretty simple exercise and one worth doing. Okay, so I guess the one word answer is induction. Okay, let's see, what else is there? For exams, can we use pseudocode? Yes, though read the question. If the question asks for Java code, you give Java code. If it asks for pseudocode, give pseudocode. I would suggest reading the question. Let's see. Okay, good. I think that is, do I accept Python as pseudocode? Only if I can read it without knowing Python. As in, the goal of pseudocode is to communicate with someone who doesn't necessarily know a particular language. Okay, good. I think that's it for today. As I said, on Wednesday, we will talk about merge sort, and after that, we will be going on to quick sort. So that is it for today. As usual, I'll stick around for 10 or 15 minutes if there are any more questions you want to ask in person. And after that, have a good week. Thank you.
Prof, are there any proof questions in the exam?
Sorry, can you repeat that? I didn't hear you.
Are there any proof questions in the exam?
Yes, I certainly might ask questions on the exam to sort of why things work and to prove things. But I will also remind you that any question that you ask me along the lines of, is X on the exam? The answer will always be yes. Any question you ask of, is this on the exam? The answer is pretty much always yes. There are two reasons for that. One is because anything we talk about is fair game. And second, because I don't want to obsess and spend a lot of time worrying about what's on an exam. Obviously, I'll talk more about exams when we get to exams.
Okay.
Okay. Is quantum mechanics on the exam? Why, yes. Let's see if we can cover that. Is there a lecture next week? So there'll be the usual Chinese New Year holiday. On days that are university holidays, there will not be lecture. On days that are not university holidays, there will be lecture. Will we be looking at any non-comparison based sorting algorithms? That's a very good question. If there were time, I would enjoy talking about some non-comparison based sorting algorithms, but I'm not sure we're going to have time for it. If we do, it'll likely be at the end of the year when we get to some of the sort of interesting, more advanced topics. Okay. There's an interesting question here of why is big omega not the same as best case time analysis? So the point is, this is where you have to be careful to say what you mean. So, I mean, big omega, big O, these are actually just mathematical functions that say something about whatever it is you're talking about. So just by themselves, they're not talking about best case, worst case, or anything. So I can, for example, I can say that the best case running time of BubbleSort is order n. That's a perfectly reasonable thing to say, right? The best case running time, that is the time of BubbleSort on the best possible input, is big O of n. Okay. It also turns out that the best case running time of BubbleSort is omega n. There is an input. So omega n tells me that it's at least n, and big O of n says it's at most n. But I can talk about either with respect to big O or big omega. And so in general, you have to make sure that when you have to make sure to specify whether you're talking about best case and worst case, and you have to specify, do you mean big O, meaning the time you're talking about is less than this, or omega, the time you're talking about is at least that. Okay. But it's a very good question because it's easy to confuse them. Everything in the world is either a goblin or not a goblin. I think that's a true statement. Yes. Should we not confuse big O and omega with best case and worst case? Yes, this is what I was just saying. That's right. Big O is just saying that whatever function you want is less than, or you should think of it as less than or equal to that. Okay, the definition is a little more precise than that, but roughly big O says whatever this is less than or equal to that. While omega says it's greater than or equal to that. Mm-hmm. Can I give an example where theta is different from big O? Sure. So BubbleSort in the worst case runs in order n cubed time, in big O of n cubed time, and big O of 2 to the n time, but it does not run in theta of n cubed time. It runs in theta of n squared time in the worst case. Okay, so if I say that the worst case running time of something is theta, it means it is both at least that and at most that. Why is the stability of a sorting algorithm important? That's a good question. So stability is a very interesting property because sometimes you want to sort by more than one index, right? In a real database, you might have multiple indexes that you want to sort by. First I would like to sort by last name, or first I want to sort by age, and then I want to sort by name. Okay, so I have multiple indexes that I want to sort by. And if I have a stable property, that means I can do my sorts in order. Whereas if I don't have an index, then I cannot. Sorry, if I don't have a stable sorting algorithm, then I cannot. If I don't have a stable sorting algorithm, every time I sort by something new, it might screw up all the rest of the things that I wanted to sort by. Whereas in a stable sorting algorithm means that each consecutive sort leaves the previous sorts alone. Okay, I might go through an example of that relevance for stability sometime next week, or maybe during a tutorial or recitation, because that's actually a very good question. Suppose we have a data type which consists of 2 comparative quantities. We want to sort with respect to the first, then the second. Yes, this was related to the stability of a sorting, sort of why it's important. Okay, I'm worried I'm bad at determining time complexity. Can we go through the complexity of BubbleSort again? Okay, I mean, BubbleSort is not the most exciting example here, and it involves probability. So it adds a few things over, most of the algorithms we're talking about. But for BubbleSort, at least, the point was BubbleSort did a bunch of iterations. In each iteration, it chose a permutation, and then it checked it. Okay, so there are two questions that we have to ask here. One is, what is the cost of each iteration? And the second is, how many iterations do we have? So how many iterations? So each iteration has a 1 over n factorial probability of choosing the right permutation. And so this means that in expectation, the expected number of permutations is going to be n factorial. Okay, and that's just a probability calculation. So that's the number of iterations, and linearity of expectation means that we can actually separate this, by the way. The second issue that matters is, what is the cost of each of these? How expensive is it to choose a permutation? In practice, it's probably going to be theta n time. How expensive is it to check if the permutation is good? That's also going to be theta n time. And so the total running time is the cost of each iteration times the number of iterations. So we have n factorial iterations times theta n cost per iteration, and that's where I came up with order n times n factorial. Okay. Is there any update for our midterm dates? Alas, no, there's a huge mess because everyone has their midterms on the same days. I will announce that in the next couple days because we need to have this decided as soon as possible. I'm very concerned that we don't have midterm dates right now. This is very upsetting, and I will try to remedy that as fast as I can. Yeah, if we get 50% on each problem set, will it still be enough to get to level 35? I don't know the exact amount you need on each problem set, but what I can tell you from experience is that a large fraction of the class gets to level 35. Okay, so instead of worrying about 50% on each problem set, how about you try your best to do as well as you can on each problem set, learn as much as you can from each problem set, and then hopefully the rest of it will work itself out. How's that? How's that for a deal? But really, it ends up not being a problem. Okay. For worst case examples, is it possible that the big O and big omega will be different? So I think, I mean, again, let's take BubbleSort. BubbleSort's an example. I can tell you that BubbleSort in the worst case is big O of n cubed. BubbleSort in the worst case is also omega of n to the 3/2, right? Right, but both of these are true statements, and BubbleSort, it turns out, is theta of n squared, which happens to be in between. Okay, so again, and these are all worst case. This is all about worst case, not wash closet, worst case. Okay, so the point is that these different notations are references to, you should think of the running time as being less than or equal to n cubed. You should think of it as being greater than or equal to n to the 3/2 and sort of approximately equal to n squared. That is the sort of right intuition for how to think about what we mean by big O, big omega, and theta. And again, all of these are talking about on the worst case input. I see potential slowest algorithms. We can talk about those on the forum. Could you go through why the expectation j/2? Yes. So I'm going to answer your second comment first. I have trouble coming up with a solution for the weekly puzzle. So no, this is not something you should be concerned about. I think this is a really tricky puzzle and a really counterintuitive one. It took me a little bit to figure this one out. So the puzzles of the week tend to be, well, they're often hard. That's often the point of them. But I think it's a really neat probability exercise. So as I said, I hope we'll discuss this on the forum and go over sort of how how and why it's true, because personally I found it super surprising when I saw this. Okay, let me go over the other question. The expectation for j over 2 in a randomly sorted array for insertion sort. Let me go back to that if I can. It was back here. Here we go. Okay, so one way to think about what insertion sort is doing, right? Let's think about insertion sort for a sec. We start out with a completely randomly sorted array. Okay, and we're now this far through our sorting process. And I want to say, how far are we going to move this item back in the sorted prefix? Okay, so the first thing to note is that this sorted prefix is essentially a random set of items that came before 7 in the array, right? Why is it a random set of items? Because we took a random permutation of the array. And so the items that were put into this prefix are just those items that happen to randomly be chosen there, right? And notice that insertion sort has not changed it's not taken anything from here and put it over here, right? Insertion sort has only done stuff on the prefix. Everything not in the prefix is still not in the prefix. The prefix is still completely just a random set of things, okay? So once you realize the prefix is just a random set of things from the array, then hopefully what you'll realize is that it's equally likely that 7 goes anywhere in this list, right? This list could have been like 1, 83, 124, 207. And so 7 is going to go over here. Or maybe this prefix was like 1, 2, 3, 5, 9. And so 7 goes over here. So the key insight, the key thing you have to convince yourself of is that 7, because it was a random array, 7 is equally likely to go in position 1 or position 2 or position 3 or position 4 up to position j. So there's a 1 over j probability that it gets moved all the way back here. And there's a 1 over j probability it gets moved here. And a 1 over j probability it gets moved here, and so on, and to a 1 over j probability that it's here. Okay, so now we can calculate what's the expected cost. How far do we expect that we have to move it? So the expected value of how far we have to move it is just going to be the sum over the positions, no, not j. Please don't use j for that. I need a eraser. Don't use j. The sum over some k if I want to put it in position k, it needs to go to j minus k, and it goes there with probability 1 over j. And so if you think about what this is just 1 over j times 1 plus 2 plus all the way up to j. And so it is just going to move j slots back, is the point. And so what this ends up working out to is j over 2. Okay. Great. So again, hopefully and I mean, this is some math, but the intuition here should be that if it's equally likely to be in any of these positions, then on average, you can think of it as being in the middle. Okay. Hopefully that helps a little bit. Okay, I'm just continuing through the questions. Then for the worst case, a tight big O and tight big omega will be the same. Well, in particular, when I say that something is tight, what I'm really saying is that it's theta, right? Like when I say that this is order n squared and it's tight, what I'm really saying is this is theta n squared. So the word tight is kind of contradicting the big O or big omega, where it's adding to it and telling you that really I meant theta. Is there even an absolute slowest algorithm? Well, in some sense, obviously not. But in some sense, there is a sorting algorithm that can be as slow as you want it to be. But yes, in some sense, in that there are an infinite number of integers, you can always find one that's larger. You can always take an extra step. Is there ever a case where the big theta doesn't exist? I mean, there are there are certainly algorithms that are unbounded in the sense of their scaling keeps changing, and you don't get a nice sort of upper bound on things. There are certainly functions that are not computable, and a not computable function will not have a computable function as an upper bound. So I guess there are cases where, big theta doesn't exist, at least not for computable functions. But I'm not sure if there are any interesting cases, basically. I think that's, yeah. In general, we're interested in functions that have sort of, interesting computable running times. I mean, what about a function that looks sort of like this, right? Where it's sort of the running time is oscillating in some unbounded way that's growing out of control. You could certainly imagine weird cases like that where you can't bound things. Okay. In that case, don't we have to assume that all the numbers 1 to 6 are initially present in the array? I think this is about the insertion sort average case analysis. And so in general, no, because 7 is also a randomly chosen element. Another way to think about, I mean, I chose 7, but that's confusing. Another way to think about this is this prefix here is a random permutation of the elements. If you look at any subset of the elements in the array, when you did the random permutation, that subset will also have had a random permutation. So whatever this next element is, you can think of as having been drawn from a random permutation of this prefix. Okay, but I mean, you're right. Once if you condition on the fact that this is item number 1, then it's item number 1. So you can't condition on the fact that its value is 7, because then certainly it's not going to be true. But it's equally likely to not be 7 as to be anything else. Okay. But yes, again, in some sense, the right way to think about it is as a random permutation of the subarray. A function is big theta of itself. Yes, I think by definition, a function is big theta of itself, always, not even in most cases, right? Sorry, I'm going back and forth between the big theta questions and the insertion sort analysis, but hopefully it's clear to people now. It looks like most of these things have been resolved. Cool. Any more questions? Any more questions? Any more questions? Okay, then I think we will stop there for today. Have a good rest. Oh, here's one more question. Is it possible for a type big O to be different from a type big omega? Again, I think when I say that something is tight, what I kind of mean is that it's theta. And if it's theta, then it is both big omega and big O, right? The word tight essentially is saying that it's theta of that. So that's, I think, the right way to interpret the word tight. Okay, so I'm going to go. Have a good rest of your week. Have a good dinner, and I will see you all on Wednesday. Take care.